Hello and welcome everybody. I'm Sam Young. I'm the practice manager for data science and AI at the Energy Systems Catapult. Welcome to this webinar. Just a few housekeeping things to start with. The session is being recorded, so you'll be able to see that afterwards. Please put questions in the chat and we'll pick up some of them as we go, and we'll also have time for Q&A at the end as well. The topic of this webinar, hopefully you know, but is details on the methodology and findings from RetroMeter in terms of how to actually calculate metered energy savings. There'll be three of us presenting, myself, Connor and Paula, who will introduce themselves as they arrive. I'll start by giving kind of an overview of what is metered energy savings, how have we been joining together some different methodologies, and then Connor's going to introduce the first two components, and Paula will cover the last. We'll hopefully take about 45 minutes and then have 15 minutes at the end for questions. So let's kick off. What are metered energy savings? So the key question that metered energy savings are trying to address is measuring how effective home fabric retrofits are. Currently, they're assessed using kind of modeling tools, SAP-based type modeling tools, to estimate how much energy will be saved. But we can do a lot better than that by actually looking at, well, how much energy was consumed pre and post retrofit. And that kind of gives us an idea of how effective the energy savings are. We've been focusing on a narrower kind of a subset of properties to do this for, which represent the largest subset of homes. So homes with gas heating that have gas smart meter data, which about between half and 2/3 of homes have gas smart meters, and kind of external temperature data, which you can get from weather stations, but not requiring kind of pre-retrofit internal temperature. There's kind of alternative ways for measuring energy usage and kind of building fabric improvements if you do have pre-retrofit internal temperature, but lots of homes don't. The data sets that we've used are working with Hildebrand. There's a smart meter data set with 17,000 homes in total, and we've narrowed in on that to kind of 3,000 homes which have more than 2 years worth of data, because we need 2 years worth to evaluate the methodology. We also have for the physics-based component of the methodology data published as part of the SMETA project, where we have 15 homes with a known heat transfer coefficient and smart meter data and internal temperature data. We've been using those for developing the model. There were meant to be 15 more that were published that we could use for validating the model, and that publication keeps being delayed a bit, so we're hoping that we'll get those soon. And then some living lab homes with internal temperature data and smart meter data as well. The way that our methodology has been developed is to focus on starting with the base of OpenEEMeter, which is an existing open source method used in the US. And that kind of corrects for weather and time of year and that kind of thing. But it has limitations because it can't account for external factors like price or COVID and big kind of one-off system countrywide events. So we've leveraged some of the kind of like existing US work on how do you apply comparison groups to OpenEEMeter homes that can control for those external factors. But then the third factor that we also need to kind of start to try and quantify is comfort take back, which is where you have a retrofit and then someone changes their temperature preferences after the retrofit because their energy now isn't costing as much. They may warm their home up a bit more. And that's where we use a physics-based methodology to combine with the others that gives us some ability to quantify that. I wanted to, before we dive into the detail, talk a little bit about how we're assessing the accuracy of these models. So imagine here that you are firing at a target, and we have here kind of 4 different targets. clearly target A is the best. Everything is focused, and it's focused around the center. Target B, well, things are still quite tightly together, but they're off center. Target C, well, the average is still in the center, but it's actually really quite widely scattered, and you wouldn't call it accurate. And target D is the worst of both. It's kind of not centered on the center of the target, and it's quite scattered. And so when we're looking at evaluating the models, we're looking at both of those dimensions. So we have bias, like, is this on target? Is this in the center? Which in terms of metered energy savings is around, does this over or underestimate the overall savings for homes? And we measure that with a metric called NMBE, normalized mean bias error. So when you hear NMBE kind of being referred to throughout the presentation, it's like, are we overestimating? Are we centered on the truth? And then variance, which is how consistently accurate is this? Kind of like how scattered around are the results? And so that's measured with a metric called CVRMSE, the coefficient of variation root mean squared error. So when you hear CVRMSE being talked about, that's the, well, how scattered, how uncertain are the results? So hopefully that sets the scene for the details of the methodology. And I'll hand over to Connor, who's going to talk us through the first and second components. So Connor, over to you.
Thank you very much, Sam. So good morning, everybody. My name's Connor Galbraith. I'm a data scientist, part of Sam's team at Energy Systems Catapult. And as part of the RetroMeter project, I was responsible for looking at the first two methodologies that Sam introduced in his slide earlier. So applying OpenEEMeter and the comparison methodology. So firstly, we're going to go through our findings and how we went about testing the US-based CalTrack standards and the open source implementation of that OpenEEMeter on our data set of properties. First slide, please. So we've been talking about counterfactuals up to now. So I think it's going to be important to really visualize what they mean in a metered energy savings context, because they can seem a bit esoteric when talked about in the abstract. So for each property in our data set, we have a baseline year, which is 1 year, up until the point in which we are assuming an imaginary retrofit, and then a year's worth of reporting after that, from which we can evaluate the real impact of the retrofit on the energy consumption of the property. Now, our data set doesn't have any retrofits, so our hypothesis is that the counterfactual should be predicting the energy usage after our imagined retrofits at the midway point of the 2-year period. So what you can see in this graph is the blue line representing the actual observed meter readings, the gas consumption on a daily basis for this property, and the red line being the counterfactual energy consumption prediction from the OpenEEMeter package. And this is based on fitting a series of regression models to the property's consumption during the baseline year, and also looking at the hourly external temperature and some calendar effects such as day of the week and the season of the year, in order to predict what the energy consumption in the reporting period will be when you only have the external temperature readings. And the idea is that in practice, this will be done on a rolling basis, so either daily or monthly, or indeed waiting until the year is up and then running the model of the entire year at once. So this is an example of a property where the fit in the reporting period, the red shaded region on the right, was quite good. You can see this gave us a CVRMSE of 0.19 or 19%. Remember that the CVRMSE is an error measure, so we want that to be lower, representing a higher accuracy. So if we go to the next slide, this is an example of a property where the counterfactual hasn't done so well. And we've seen that when the property doesn't behave as the model expects it to in the face of the temperatures that it sees, you end up with a counterfactual that fails to predict the actual consumption in the reporting period particularly well. Now, on the next slide, the period over which we tested this over our data set of roughly 3,000 homes that were valid for us to run OpenEEMeter on. The most important periods of the year are the winter periods, because that's where the vast majority of gas consumption occurs for each property. Now, the green line shows the average monthly temperature for the baseline period over the winter period from October to the end of March. And you can see that in the reporting period the year after, the winter of 22-23, it was notably colder in the months that matter, i.e. December, January and February. So given that OpenEEMeter only uses the external temperature and some calendar effects to predict the gas consumption, you would expect it to forecast a higher level of gas consumption in the reporting period because the temperatures are colder. However, if we look at the next slide, we find that in reality, this is not what we see at all. So the first thing to focus on here is the bar chart component of the graph, where green is the average gas consumption over all properties for the baseline period, and orange being the average monthly gas consumption for the reporting period. Now, even though it was colder, on average, the properties used considerably less gas, particularly in October, November, and February, and mildly in January as well. And as you may all remember, we had a particularly bad gas price crisis over that winter. You can see this in the lines that are on the secondary y-axis on the right. The retail gas index almost doubled from the winter of 21 to the winter of 22. And this had a very deleterious effect on how consumers appeared to consume their gas, as you would expect, despite it being colder. And this is a key externality that OpenEEMeter on its own can't account for, because it only sees the external temperature. So on the next slide, we look at the error over all the properties when aggregated to a daily, a monthly, and an annual level. And just for comparison, we have here in orange as well the results from the Metered Energy Savings 2022 project, which used a much smaller cohort of properties, but crucially did not include the winter with the gas price increase. So we can see that there's a very high variance in error, particularly for the daily level of aggregation, with a median error of around 50 to 53% for daily. Now, those familiar with the ASHRAE guidelines will know that the hourly acceptable error for that is around 30%, and at the monthly level it's around 15%. They don't stipulate a daily allowable error, but even if they did, and it fell somewhere between the hourly and the monthly guidelines, the performance of OpenEEMeter on this data set is well above what would be acceptable for real metered energy savings applications. So on the next slide, the other component of interest is the bias that Sam introduced as the NMBE figure. Now, in this plot, each point represents a property, and its CVR MSE and NMBE figures at the daily level are plotted with the bias on the x-axis. Now, what you may notice is that the majority of the properties are clustered on the right-hand side of the graph, to the right of the zero bias points. Now, what we're seeing here is the influence of that price spike over the winter of the reporting period, leading to a significant systematic overprediction of the consumption during the reporting period. And this is seen by the clustering to the right. Now, this is going to be important when we come to look at what the comparator methodology does to address this systematic bias. On the next slide, we are going to get into just that right now. So we need a approach for mitigating the fact that OpenEEMeter only looks at temperature. It can't account for externalities that affect the consumption of all properties in a jurisdiction, a country, a society, a market. And one way to do this is to take a group of properties that haven't had a retrofit and compare their energy consumption to a property that has had a retrofit, and to look at the differences between the consumption in the baseline, so the reporting period for those comparator properties, and deduct it from the candidate property. Now, those familiar with looking at the difference of differences approach in kind of causal analysis should recognize this. What we're doing is matching comparator properties to a candidate property based on a range of possible different factors, such as the property type, the age, the built form, but also quantitative similarity measures, such as the similarity of their baseline consumption profile, or even just how much gas they consumed overall. And once you've identified a set of similar properties, what we do is we fit OpenEEMeter to each of them as before, and we look at the error between the counterfactuals and their recorded consumption during the reporting period and deduct that error from the counterfactual fitted to the candidate property. Now, this diagram hopefully helps visualize that process a little bit better, because it can be a little bit fiddly to keep track of what is being fitted to what. There's a lot of words that begin with C that doesn't help. So what we're expecting in this case, because we know that there are no retrofits fitted to any of the properties in our data set, we expect the impact to be zero. So much like the null hypothesis in the testing of the OpenEE methodology alone, once we remove the comparator properties error from the candidate property, we expect the accuracy to tend towards 100%. We expect it to get better at predicting the consumption during the reporting period. So on the next slide, we can see what this looks like in practice. This is the aggregated monthly consumption for a given property. Their metered consumption is in red, and the predicted consumption from just running OpenEEMeter by itself is the blue line above it, and you can see that systematic over-prediction there. However, once we apply the comparator approach, which I'm going to go into more detail on in this section, we can see that it pushes the counterfactual closer to the red line, which is the lime mint colored line just above it. And this is what we want to see over, ideally, all of the properties. Not just improving the accuracy, but also removing that systematic bias caused by the price change externality. So on the next slide, we're going to start by highlighting the importance of how high quality the matching is between the candidate property and the group of comparators that you select to operate on. Now, just looking at matching properties based on whether they're detached or semi-detached, roughly how old they are, maybe their EPC rating, we find that the comparator approach without smart meter, which is the green boxes here, actually performs worse than if you just used OpenEEMeter on its own. Now, this indicates that taking properties that have the same built form, a property type, age, and EPC rating doesn't give you enough information about the similarity of their consumption behavior to actually be useful in applying this comparator approach. So instead, we look at some more sophisticated approaches, which on the next slide we'll go through. So before we get to the properties that we use to match over, however, it is worth noting that even though the accuracy worsened when we matched on those property archetypes, the systematic bias is removed. So you can see this in that the orange dots, which represented the individual property readings that I showed on the similar smile-looking graph previously, are now symmetrically distributed around the zero line. And this indicates that on average, the systematic bias is removed. We just have a bias component now for each property, which is model specific and not, property specific and not model specific. So on the next slide, we have summarized the performance increase that we get when we use some more sophisticated measures for matching the comparator properties to the candidate properties. And these include looking directly at the similarity of the baseline consumption profile at the daily level between each property. So quite literally, how close are the time series together? If they're very close, fantastic, you're a matched property. And using this, we were able to get an almost 80 to 90% improvement, or in this case, a 30 percentage point increase in accuracy. You can see the median CVR/MSE using the best features and parameters is shifted down quite a way. And as well, it maintains that ability to strip away the systematic bias that we saw from the price increase as well. And on the next slide, we can also see that the approach of combining the candidate properties into portfolios increases the performance even more. If you think about it from the perspective of grouping comparator properties together in order to reduce the noise in their individual consumption, well, we can do the same for the candidate properties and aggregate their counterfactual as well to reduce the noise even further. And this gives us accuracy at the annual level with a 25 property portfolio of around 4%, which is a very big improvement on using OpenEEMeter by itself. And portfolio approaches are going to be very useful when it comes to things like large numbers of properties that are owned by and operated by a single manager who may be able to access more favorable funding terms for retrofits and other interventions that are done at a scale larger than an individual property. And on the next slide, so concluding from all of these, the comparator-based methodology, we established it as the way to go for operating in the UK. There are some studies in the US that have shown that OpenEEMeter by itself gets incredibly good accuracy, but that tends to be when it's applied to properties on the West Coast with electric HVAC systems, both heating and cooling, more established behavior, less volatile prices, that kind of thing. Now, one of the wrinkles in all of this is that we have done this analysis as part of the RetroMeter project on a static smart meter data set. In practice, what is going to happen is that at the point where a retrofit is finished, okay, we already have for example, the 12 months of smart meter data prior to the retrofit for fitting the model over the baseline period. But to keep the evaluation rolling through the reporting period, we also need to maintain a repository of comparator homes that have not had a retrofit and will not have a retrofit for the duration of the reporting period of the candidate home. And we are in the middle of exploring various ways in which we might be able to maintain this in practice. We're speaking to some commercial partners that may be interested in this, but it's a pernicious problem because we are attempting here to create an open source methodology that the metered energy savings community can run with and improve upon. Given how difficult it is to work with smart meter data in the UK, particularly live updates of smart meter data, we don't want this to end up being gatekept and siloed by a small number of commercial actors. So this is something that we're actively exploring currently to make sure that this methodology could be taken forward in the future and maintained rather than just sitting in the vaults. Now, there have also been some other studies in the US that have tested the influence of pool size, looking at, for instance, limiting the pool of available properties to select your comparators from like 50,000 down to 10,000 down to 5,000. It's a lot easier to get hold of smart meter data in the US because it's essentially managed by the network operators and suppliers. We didn't find it to be a problem in this data set, despite the fact that we were only operating with 3,000 properties, which is a good sign. That bodes well for making it easier to implement and maintain in practice without needing tens of thousands of properties worth of data. Now, one thing that the comparator methodology does not account for is when people get a retrofit, they save some money and realize, oh, we can turn our thermostat up a little bit now because we're saving some more money. And this is where comfort take back comes in. And Paul is going to talk about how we try to account for that in our modeling.
Thanks, Connor. Hello, everyone. I'm Paula. I am also a data scientist at the Energy Systems Catapult. I hope you can hear me okay. My voice is a little bit shaky today. I'm still recovering from a cold. Yeah, I'm going to talk you through the physics-based methodology, which has the aim to calculate the comfort take-back. Next slide, thanks. So we want to calculate the comfort take-back, and the way we do that is we have two counterfactual energy demands. One where we don't take into consideration the internal temperature, which is the comparison-based methodology that Connor just talked you through. And the second one is one where we do take into account the internal temperature, and this is this physics-based methodology. By subtracting my physics-based methodology from the EEMeter counterfactual, we can estimate the comfort take-back. And here's how we calculate the counterfactual energy demand for the physics-based methodology. First, we calculate the pre-retrofit HTC for each house only from smart meter data. The HTC is the heat transfer coefficient, which is a thermal assessment of the house. And then I use that HTC and the pre-retrofit HTC and the post-retrofit internal temperature to estimate the counterfactual energy demand. So this is the energy that we would have seen if the occupants had been heating to those temperatures without doing the retrofit. And then we compare it to the comparison-based other counterfactual and get the comfort take back, or also the comfort boost, because we're increasing our comfort and our temperature. So first we need to, next slide please. First we need to calculate the heat transfer coefficient, which, as I said, is a measure of the thermal performance of a house. A low HTC means that we need less energy to heat our homes. And kind of for context, the average HTC in the UK is 330 watts per Kelvin. To design our model, we used the 15 houses from this meter data set, which had known HTC values, co-heating HTC values, where a co-heating test is a standardized test to calculate the HTC. However, it's something that is hard to do at scale because it's relatively intrusive. It requires the occupants to leave the house for 1 or 2 weeks at least, and have an electric heating turned on the whole time. But having these co-heating HTCs means we can use them as a ground truth to verify our model. So the way we get the HTC is by regressing the difference in inside and outside temperature on the x-axis against the power used. And the slope of that regression line represents the HTC, which in this case is 207 watts per Kelvin. In general, if we use the internal temperature, so the difference between internal and external temperature, we get relatively good results. They're quite reliable across all the houses, and we get a high R-square values for all the houses as well. However, pre-retrofit, we don't actually have the internal temperature. So what we do instead is we regress only on the external temperature. That relies on the assumption that the internal temperature is constant, because that would just be a shift in the regression line. However, what we found is that without the internal temperature, our results are a bit less reliable, and that we also tend to under-predict the HTC value. So on the other slide, we had a modeled HTC of 207, and here we only have one of 148. And the co-heating test for this property is 213. So with internal temperature, we get a way more accurate prediction of what the actual HTC is. We think that the reason for this is that there are some days where there's very little heating. As you can see on the graph on the right-hand side, where we can see the internal temperature distribution, there are some days where the internal temperature is only about 16 to 18 degrees. And these are the days kind of on the right-hand side. Every dot represents a day. So the circled in ones are the ones that we think cause a problem for our model. We can mitigate this by eliminating the days with low internal temperatures. But again, we don't have the internal temperature, so we need to approximate those days. So what we want to get rid of are the days in that shaded area, the pink area. The way we do it is we regress on our data, and then we look at the residuals and filter out the negative outliers of these residuals. On the next slide, you can see an example of how that's done. So here, all the little crosses in red are the days that we're not considering because we think that the internal temperature is too low. The red slope is the original estimation of the HTC value. The blue line is the improved HTC prediction with the outliers removed, and the yellow line is the HTC, the co-heating HTC, and you can see that the blue line is, the slope of the blue line is much closer to the slope of the yellow line than of the red line. This still isn't perfect. However, in general, we see that the HTC performs much better if we take those outliers, if we filter out those outliers. So here we are comparing the modeled HTC results on the y-axis to the co-heating HTC results on the x-axis. And on the left, you can see the results without any outlier adjustment. And we can see that we're under-predicting the HTC for all of the homes. You can see that because all of the crosses are below the dotted line. On the right-hand side, we're comparing the modeled and the co-heating HTC but this time the outliers have been filtered out, and we can see this gives us a better fit, and the model is slightly less biased as before. So now that we have the HTC values, we can use them to predict our energy usage. Just go. So we calculate the energy demand by using the HTC. We multiply that by the difference of the internal and external temperature. So now this is post retrofit. We have the internal temperature. We then also need to take into account the different gains. So we have the solar gains, which is the sun heating up the house, and that means us having to heat less. Electricity gains, which is electricity that we consume, that we assume then dissipates as heat in our homes. And lastly, the base load, which are things like cooking, showering, hot water. Next slide, please. So here are the results from the comparison-based methodology and the OpenEEMeter methodology, on both in pink, and then in green you can see the results of the physics-based model when we are using the co-heating HTC. The mean CVRSME is even lower, so that means for this data specifically, it is more accurate. But again, this is only tested on 15 houses, so kind of we need to keep that in mind. And there's still a very slight overestimation as the NMBE is just slightly above 0. So if we now use our estimated HTC value, not our co-heating HTC value, but our estimated value, we can see on the right-hand side in blue and yellow that we're getting a bit less accurate with the prediction. But in general, if we use the outlier adjusted HTC estimation, our model is now slightly under predicting, but it's not very biased. Whereas if we don't adjust for the outliers, our model is quite significantly underestimating. So very biased. Here are the results for the individual houses. On the left-hand side, you can see the results using the co-heating HTC, and on the right, you can see the models using the modeled HTC. And this shows us that our model works for some houses, but definitely not for all houses. However, if you aggregate the results, we can see that our NMB and CVRSME is relatively similar to the comparison-based methodology. So we get decent results at an aggregate portfolio level. Overall, the physics-based methodology performs similar to the comparison-based methodology. However, the results vary too much on a per home basis to be able to calculate the comfort take-back for an individual home. But we do think that we can use it to calculate the comfort take-back at an aggregate portfolio of homes.
Thanks very much, Paula and Connor. I'll kind of talk through some overall conclusions from this, but please do put questions in the chat if you have any, and we'll get to them in a minute. So at a high level, kind of the conclusions that we come to are that you can use only smart meter data and weather to model gas demand, that comparison-based methodologies do work well for kind of accounting for external factors such as energy price changes, and that it's probably important if we're expecting significant price fluctuations over time to use those rather than the weather-only models. But there's this big challenge around the fact that they require ongoing access to smart meter data from non-retrofit homes, which is currently a challenge in the UK. And then physics-based models can be combined with comparison-based models to estimate comfort take-back. It seems like that's feasible, but probably again only on a kind of portfolio level. And having internal temperature pre-retrofit does improve the accuracy, but it's not kind of vital. You can still get something out without it. But the big challenge with all of these results is that the uncertainty is relatively high if you're looking at a single home. And so using it as a kind of something that's focused on communicating with specific householders, this is how much you have saved, or quality assuring the work on an individual home will be quite of a challenge. But you don't need a huge number of properties for the models to be giving you uncertainties that are pretty small. And so we're talking kind of like, even when you went from 1 to 3, 5, 10, 25, like small numbers of properties reduce the uncertainty quite dramatically. And so that means that for a lot of practical purposes in terms of financing and that kind of thing, you can probably aggregate properties together in a way that is useful. So that's the overall conclusions from the work. Hopefully you've kind of understood some of the methodology, though we haven't gone into in excruciating detail. Are there any questions that people would like to ask? I'll give people a minute or two to drop questions into the chat if you have them. Otherwise, I'm going to assume that we have explained everything so clearly that you have no questions. Okay, if the predicted saving is under 25%, do you think you could accurately assess if the savings are achieved? So this is where I think if the answer is like the predicted saving is under 25% for an individual home, then I think the answer is you can't do a good job of assessing whether that saving has been achieved. I think if you have a whole load of homes and you're doing similar interventions on them, and you think that those interventions should be leading to a 10% or a 15% saving, then well, actually you can get the uncertainties down to the 4 or 5% range by grouping together a bunch of homes. And so you can assess overall, have the interventions on that group of homes reduced energy usage by 10%, 15%? Yes, I think we can do that. I think where it's more challenging is if you're looking at the like, oh, well, we've got homes that are like, we think the energy efficiency savings are 3%, 4%, 5%, then the kind of uncertainty is comparable to the level of saving that we're expecting. Yes, the webinar recording will be available and shared later, and we'll also be publishing kind of a report with kind of a written version of our findings and details there. Okay, if you needed to get a very reliable savings figure for an individual home, could the methodology allow ways to make bespoke adjustments to the baseline for that one home? So that's a good question. I guess we haven't really talked about the different alternatives to this as a methodology. So one of the reasons that we use the smart meter only HTC calculation is we recognize that there are other existing products out there that are focused on how do you measure the HTC, and you put some kit in with internal temperature sensors and that kind of thing. And so you can use some of those to get a more accurate version of the HTC calculation. And so you can kind of like make those comparisons based on HTC. The demand model shows that you can, if you've got a very accurate HTC for many homes, you can probably get quite an accurate estimate of demand. So it's kind of like, actually, if you need accuracy for an individual home, the route of, well, let me go down the physics-based modeling, get as accurate a measurement of HCC as I can, and then kind of put that in would be one route. Another alternative would be if you had a home and you wanted to kind of like improve the accuracy of the modeling for that individual home, you could try and train the model on more of the on a longer period than just a year, and kind of do some train it on the first year and then do some calibration on the second year to try and kind of manual adjustments on that. But that's not really kind of we haven't thought in lots of detail about how you'd do that and what the kind of how you'd avoid kind of tricking yourself into thinking that you'd fit very well for the property. I think the reality is, if you're trying to get an individual property measured, like understood in lots of detail, then you probably have to go down the more sensors, build a physics-based model of the home. This approach isn't really designed, like the OpenEEMeter in comparison group approach isn't really designed for allowing you to like tweak and tweak and tweak and tweak and tweak on an individual home level. Do you expect that the models developed are suitable to evaluate energy flexibility measures at the half-hour or hourly level too? Or is the use case specifically for energy efficiency retrofits only? So there's two halves to the answer to this question. The first is that we focused on gas, specifically because gas doesn't require, well, partly because gas doesn't require time of use, and so you can model everything daily, which allows you to get kind of like makes the model easier, and you can get to a better accuracy. The OpenEEMeter methodology does have modeling of hourly and kind of hourly electricity or hourly gas. So it is possible to extend it into that time frame. The thing to consider when we're talking about energy flexibility measures, and this is kind of like the other half of the question, is when you're looking at flexibility, what's the counterfactual that you really care about? What's the kind of the baseline where you assume the no flexibility has occurred? Because with general kind of demand response type flexibility, you can get more accurate baselines by looking at recent days, recent weeks, than this approach, where you have to look back and kind of model based on external temperature and what they did a year ago and patterns in the days of the week and all of that kind of stuff. So this methodology is designed for big one-off changes to a property that are going to change the whole usage pattern of that property, rather than short changes in the kind of flexibility where you could like use something you could use recent days to understand that. If we do extend this to an electricity time of use mechanism, then there's the possibility that it could add in the like almost how have the overall average time of use patterns changed as a result of a retrofit or the installation of a heat pump or something like that. But it's not designed for like the individual flexibility events. More, it could be designed for kind of like the introduction of flexibility capability within a home. And it's quite common. It's an easy thing for people to confuse. And it's a bit of a challenge, I guess, for the sector as a whole, is how do we align those two methodologies and kind of ensure that we're comparing apples to apples as much as possible, when one of them has to look at the far history and one of them can look at the recent few weeks. Any more questions from anybody? If not, thank you very much, everybody, for your time. Hopefully this was useful. As I said, the recording will be made available, and we'll be publishing a written report as part of the wider RetroMeter work at the end of March. Thank you very much.